Uh, we are back after a long time. Not a long time, after a week, I think. I'm doing the next stream, so I tried to be consistent, but there are some other works that come in the path. So, okay, give me 1 minute, guys. Okay, so now we're going to solve one problem. So I think there are not much more problems left, right? Most stones, strongly connected component, Kosa-Raju algorithm, bridges in graph, and articulation point. I think only four problems are remaining, and our graph series will end. So yeah, quickly just solve all those four problems, and then we can move to code forces because, or we can start with some. Let's say I write here auto draw, right? Auto draw. Then we will start with uh, kind of DP, dynamic programming. It's kind of a hard topic, I will say, in uh, programming. Dynamic programming is considered a little hard, not little hard. It's even considered harder than graph, right? It's even considered harder than graph. Mm, so, so, so it's like this. So we will like I have some basic idea of DP and we'll solve some complex problems on DP and yeah, we'll do that. For now, let's start with this problem. So mm, on a 2D plane, we place n stone at some integer coordinate points. On a 2D plane, we place n stones at some integer coordinate points. Each coordinate point may have at most one stone. Most stone removed with same row or column. On a 2D plane, okay, we place n stones at some integer coordinate points. Okay, so we have a 2D plane and we are pointing in stones. Each coordinate point may have at most one stone. Okay. A stone can be removed if it shares either the same row or same column as another stone that has not been removed. A stone can be removed if it shares either the same row or same column as another stone that has not been removed. Okay. Given an array stones of length n, where stone I represent the location of the ith stone. Return the largest possible number of stones that can be removed. Okay. Given an array stones of length n, where stone I represents the location of the ith stone, then the largest possible number of stones that can be removed. Uh, a stone can be removed if it shares either the same row or same column as another stone that has not been removed. Okay. Mm, So okay, let's draw this, right? We have a coordinate plane. We can create a coordinate plane. It's easy. Oops. It's not a straight line. Oops again. Mm, What? Oh. Mhm. Fine. Robot. Auto draw. Scully draw. What is okay? We have undo, right? Undo, 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 undo. So, okay. So, yeah, we can do that here. So, so we have a coordinate point, right? Okay, I'll draw X coordinate and I'll draw, sorry, sorry, Y coordinate and X coordinate. Yeah, name this as X, oop, and name this as Y, right? And what we have? 0, 0, we have okay, let's point to 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 6. So we have a stone here, right? 0, 0, we have a stone. We have a stone at 0, 1, 0, 1. We have a stone at 1, 0, 1, 0. We have a stone at 1, 2, 1 and 2. So we have a stone at 2, 1, 1. This is, oops. This is 1, 2. This is 1, 2, and this is 2, 1. And yeah, just ignore this. Just ignore this. We have a stone at 2, 2. Oops, we have a stone at 2, 2. So okay. And the question is how much uh the maximum stones that we can remove, right? That's the question. Okay. So um, one way to remove our stone. Okay. Uh, yeah. Uh, we can do one thing is that a stone can be removed if it shares either the same row or the same column as another stone that has not been removed. So we can remove this stone, right? Then we have this column, we can remove this stone. Then we have this column, we can remove. We can remove this stone. Then this column, remove this. Then this row, remove this. So in the last, we are just left with one stone. But see, there needs to be an optimal strategy here because, or what we can do. Because is there an optimal strategy here? Like, let's say if I remove this. Let's say if I remove this stone first, right? and then I remove this stone first, second. So these two stones are removed, then I remove, then I have these. So I will have two stones left, right? Because this column I can remove one. Similarly, this row I can remove one. So I'll be left with two stones. So as you can see, this is not an optimal strategy, not an optimal strategy here. You can see, right? Because what was happening is that say I have this one here, this one here, and this one. So if I remove this and I remove this, then I'm left with two stones. Not an optimal strategy, as you can see. Okay. 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 So we know that we are doing disjoint set union, right? DSU, data structure problems. DSU, disjoint set union, data structure problems. So, uh, we can do one thing, right? Mhm. We can create a disjoint set. So, so let's say in this case, right? See, this is our default state. So for this stone, it can be a part of these two stones, right? One, two. Let's name them one, two, three, and four. So for one can be part of four, and two can be a part of one and four, right? Because because they have a common representative. As we do in disjoint set, we have a common representative, right? Now we are left with three. Now if I see three has row and column part as four and two, so three can also be the part of the set. So we can say that one, four, two, three are part of a single set. If these four are part of a single set, then maximum stones we can remove is the maximum set length, right? Maximum set length minus one, right? Or we can say all the sets. So from each set we can remove all stones and only one stone will be removing. So remaining stone we can easily count, right? Remaining stones will be count of set. Remaining stones will be equal to count of set, right? Count of mm, total sets that are created, total disjoint union sets that are created. Mm. I guess I'm making a sense here, right? So, okay, let's now. I think we have figured out. So we'll start coding the solution. Uh, okay. Open our solution. Okay, so we have this disjoint set, and let's revise for once. So what we were doing in our disjoint set class, we have a parent and a rank. So this is our so parent is basically the parent array is storing the parent of each node, right? Treating node as one, two, three. Then we have rank. And in rank also, what we were doing is basically storing the rank basically means the depth. Rank, I think rank means the uh, yeah, rank means the total depth, right? Total depth, highest total depth, total depth uh, is meant by rank right here. So yeah, this was the rank, and what we were doing, oops, what we were doing is basically in find. What we were doing, we were keep on iterating it, right? So if we have node, then another node, then another node, then another node, one, two, 3, 4, and if we have to find the parent of 4, so ultimate parent, not the parent, ultimate parent, then we go to 3, we go to 2, we go to 1, and then we figure out, okay, 1, then 1 comes here, here again, and again, we figure out. So in that process, what we do path compression for this. So we compress the path for this, we updated it and we connected with all the parents. If you see, mm, if parent is figured out, return, and then we were uh, so we found out the representative, right, and we were updating path compression optimization, updating the representative. And in union, what we were doing, we were, if we have two sets, right, and we have to add them one, so what we were doing, we were calculating both the ranks. And if rank of u is greater than, initially all rank is 1, right, if rank of u, uh, then we were updating the parent of u to v. And if rank is equal, then anyone can attach to anyone, and the attached one's rank increases, right? And if rank is less, then the rank will not be increased, because let's say if I have one, okay, oops, okay, one, let's say I have this node and I have another node as like this, right? So its rank is greater than this. So if I attach it to here, and I have this, I have this, and I attach it to here, right? Its rank is 2, its rank is 3. So this will be attached here. Uh, this will be attached, not with it directly here. So this rank and this rank, its overall rank has not been increased, right? So yeah, that's the concept. Okay. So I think we have brushed up the concept and we can start with solving this problem. Mhm. Okay. So we have this array. Mhm. And okay, so first thing what we will do is basically uh, yeah, so we will be now how to identify what is the uniqueness. Can you identify the uniqueness in each stone? Like can we mark them as 1, 2, 3, 4, 5, 6? So this index represent this stone, this index represent this stone, and similarly this index represent this stone, right? So we can index the stones. So 1, 2, 3, 4, 5, 6, right? Or 0, 1, 2, 3, 4, 5. Okay, so this is how we can indexing, and basically 0, 1, 2, 3, 4, 5 will be our nodes, and these are the values inside this, right? Okay, that makes sense. That makes complete sense. And now, okay, so first of all, let's create a data structure disjoint sets, right? So yeah, let's create this disjoint sets equal to new disjoint sets, and we will pass. Okay, so in n number of stones dot length, and what we can do next is basically um okay, so we have created the structure. Now DSU. Inside DSU. Let me name it as DSU. Okay, so we have created the structure and now we will traverse the stones array, right? So what we have to do is basically so right let's say if I have these four stones, right? These four stones. So I'll travel to each index and I'll look for all the columns and all the rows, and if I and join uh I'll union them, right? Union them into a single set, union them into a single set, right? Okay. So, okay, so yeah, mm, that we can do, right? Or we have this. Yeah. Okay. Okay. Give me 1 minute. I think the charger is not plugged. I'll just plug the charger. Yeah, guys, so I'm back water break. Now let's continue it, right? So, okay, so we have created our data structure and now we need to populate it, right? So, if you can see, we have this array and its locations of stones are mentioned. So, how can I how can how can I add all the stones? So what? Okay, so one solution that is coming into my mind is to uh, traverse all rows, right? Like this. Oops. Traverse all rows. It's right here. And whatever stones I found in the rows, club them into one set. Similarly, traverse all columns. Oh, not required because oh, it's required. Traverse all columns and whatever stones I found in the column, club them into one, right? Okay, so that is the solution, right? Mm, okay, so yeah, to traverse all rows and columns. How can we do that? So mm, we can use a for loop. For into row equal to zero, a row less than n row plus plus. Okay, okay. And for each row, we have all the columns, so we can mark them as 4 into oops into column equal to 0, column less than n, and column plus plus. We- Okay, give me 1 second. We have 1000, right? So, okay. Yeah, we can do a we can do a two for loop kind of recursion. And what needs to be done here, right? So we have uh rows and columns, and now um okay, now for each um okay, now but the problem is how can I figure out if it has a stone at a specific index or not? Okay, it looks like okay, so so we have yeah, we have a question on our hand now. How can I figure out mm, or I need to use a third loop, then it will be very bad performance. So, I have some stones. Should I? That's why I can be 10 raised to power 4. Okay, so we can have a grid goes to 10 raised to power 4, right? Hmm. Similarly for uh similarly for columns also it can goes to 10 raised to power 4. So can we create a normal grid of and just fill it with zeros and ones, where one means a stone is present and zero means it's empty, right? Can we do that? Zero, one, zero, one, one, zero, one, zero, one, right? Can we do that? Can we do this kind of stuff? Oh, we can do this. Yeah, that can make sense. And then we just need to traverse this stones array and it, fill this, right? Fill this up. And then we can again traverse this grid and in row fashion and in column fashion again and get all the next stream. So I get all the tones, right? NT as you said. Mhm. Yeah, that makes sense. What's the if not that, then is there some other solution that is coming into the mind? Um, mhm. Not at the moment. I think we are good, right? We can do this. Mhm. We need to do this, right? I don't think there is a alternative, or there might be, but I'm not able to. Can we just traverse and figure out? Uh, so we know that this belongs to zero throw, right? We know that this belongs to zero throw. So I can traverse all rows, and if my current stone coordinate row 0, traverse complete, row 1, traverse complete, row 2, 2, 2. And similarly for column, I can do, right? Yeah, I can probably do that. Yeah, that makes sense. So, um, but for each row, I have n, right? N is 10 raised to the power 3. So for each row, okay, I need to traverse the complete array, stones array, right? And yeah, so if okay, so if stones I sorry I and 0 is equal to row, our current row, right? If it's equal to current row, then we can do is um, yeah, we have found out a stone, but we need multiple stones, right, to join them. We need at least two stones to create a union for them. So uh, okay, so we can track of previous stones as -1 right now. And okay, so we can keep a track of stones as -1 and yeah. Okay, so if previous stones is equal to -1, then make the previous stone equal to row, right? That row. Else, which means we already have a stone, right? So we just have to union it, right? Just have to union it. So DSU, disjoint set union. We have a stone dot union, and union we have our previous stone, right? Control set. Oops. Make it as I, right? Our previous stone and our current stone will be. Oops. Okay, give me 2 minutes, guys. Okay, guys. So yeah. So we have the oops. We have previous stones and we have our current stone, right? And just union them. So it will be done for all rows. Uh, so we are unioning rows here. Similar stuff will be done for columns also. Now we will be doing unioning columns, and for that we need to call equal to 0, then n plus, and yeah. Similarly for columns also we will have previous stones equal to -1, and We'll just iterate it over, right? I equal to 0, I less than n, and I plus plus, and if stones I1 is equal to column, then yeah, can just check if oops, if previous stones is equal to -1, then stones will be equal to I, else we already have a previous stone, so we will just union them. Previous stones, comma, I, which is our current I, right? So we have union rows and we have union columns. Now we need to figure out the total number of disjoint sets we have. So how will we figure out that? So we need to figure out the total number of need to figure out the total number of PSU we have. mm, Oops, disjoint sets we have, and I'll figure out. So just iterate over this I loop. Um, Now how will I figure out how many disjoint sets we have, right? How can that be figured out? Hmm. Yeah. So that can like I think that is simple, right? So how to figure out the total number of disjoint sets? So let's say if I have two sets, right? If I have two sets, something like this. One, oops, zero, three, and four, and one, two, five, six, and seven. Now, we will have we will find out the parent. So I'll start with zero. Zero's parent is zero. Okay. Three, three's parent is also zero. Four parent is also zero. One parent. Oops, wrong array, wrong array. Zero parent is zero. One's parent is one. Two's parent is one. Three's parent is zero. Four's parent is zero. Five's parent is one. Six is one. Seven is one. And this is our array, right? So how many unique? So we will have a set, right? Parent set kind of thing, and we will just insert the set parent, right? And we will only have two unique values in that hash set. So set count will be our answer. Less than and I plus plus, and yeah. So it's easy. We will create a hash set here. and A hash set here, right? And start Add dsu dot find parent ultimate union of I, and I'll return here s dot. That is our answer, and yeah, that is our solution. Okay, so that's our solution, right, for this problem. Mhm. That is it, right? That is our solution. Mhm. Okay, copy paste it, try to run it, and not. What? So we need to give the total number of stones removed. That will be oops, n minus the solution. Total numbers of. Hmm, got it, got it. Got it, got it. Total stones minus we have the sets remaining, right? Yeah, that will be our solution. And after this, which prob? Okay, okay, it fails. It fails for one of the test case. 99 output, 99 expected 288. Okay, okay, our solution is failing for one of the test case. Give me guys 2 minutes of washroom break. I'll just come back and we'll figure out why this is failing for this. Hello guys. Okay, guys, so let's continue. What a break. The break was quite long, but let's continue, right? Hmm. Okay. So yeah, some test cases are failing. So this basically particular this test case 57 test case is failing, and so it's giving output as 99 where it is expecting 288. Okay. I think our logic is correct, right? There is nothing wrong in the logic. Because we are just we have parent, we have rank, and oh, cool. And here we need to figure out the total number of disjoint sets we have and how we are doing. We are basically finding the parent, and so if all the sets have single parent, there will be a single entry in the set, and which means there's a single set, and which means and total number of stones can be removed, right? Optimally, because uh yeah, one stone will be left, right? Yeah, but total number of stone. So I think we are missing something like the number of sets that created for us are not are less. So which means that uh so if we multiply 99 by 3 by 297, right? Okay. Um. Okay. So I was how will so the number of sets are basically less. Then so we are clubbing less. So, but I don't think so. I just what we did it we iterate through all rows and we iterate through all columns, and whenever mm, for all rows we add them into a single set. Similarly for all columns we add them into a single set. Mhm. I don't know why it's not working because it seems to me as a correct approach. Uh, I don't know why test cases are failing for this. Mm, mm, it should work, right? It should work. So, so I think in columns we are doing okay. So for columns we have n columns, and we are iterating through all the stones again, right? And if a previous stone is equal to minus one, then mm, we are updating the previous stone. Otherwise, we are just in for each column, right? We are just unioning those two, right? Okay. But why we are just unioning with previous stone? Mm, like like the first stone. Mm, can this prevent us from? Can this reduce our total number of sets? Hmm, I don't think because all are eventually added in the same set. A stone, I just add it there. Okay, I have a stone. Hmm, 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 hmm. I don't know why this is not working. It should work. Mhm. Because uh, we have column value, so column 0, then oh, it makes complete sense. Mhm, 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 mhm. So, mhm. I don't know why it's failing because you are clubbing into a single set, and whenever, let's say, this is coming right, so this will. Mhm, 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 mhm. I don't know why it's failing because for me the logic seems perfectly fine. I don't, I'm not able to figure out the flow in the logic because if let's say if I have some structure like this, right, then it create a single set because when I read through this row, this will be into a single set and mm, these two nodes will be in a single set. And when I iterate through this column, these two sets will be in a single set. And mm, when I iterate through this column, these four will be combined into a single set. Hmm. What's wrong here then? It's nothing is wrong. Everything looks fine. Hmm. Everything looks good here. No defect I'm able to figure out. Hmm. Yeah, everything looks good here. Uh, Uh, am I missing something here? I don't think so. Everything is looking good, but I'm getting the wrong answer. Number of sets that are being created is way less than expected. Hmm. Okay. Mm, mhm. So let's use this test case, right? It's a huge test case, huge, huge. And mhm. Well, let's debug this. Let's console it logs and try to figure out if we can find out some anomaly, something that can be helpful. So let's first calculate the total nodes. That we have, and then we will be then we'll just console set count DSU count count. Hmm. Okay, so total nodes is 1000 and DSU count comes out to be 901. Hmm. But uh, that so total nodes, which is 1000 minus subset count is equal to the answer, right? 298, which means total subset should be 98 or 300, which is 702, right? So this should be our total subset, like disjoint sets that should be different disjoint set, but for my answer, my I'm getting as 901. So I'm getting so as count, right? Which means mm, which means I'm not clubbing all of them. I'm missing something. Okay, okay. Um, Logic seems to me as fine, but hmm. So we are finding the parent and we do the path compression representative, updating the representative, and will find me the Mhm, 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 I don't know what's wrong here. Mm, but definitely I'm missing something here. I can. Okay, let's read the question again. I'm think. Mm, on a 2D plate, please each coordinate point may have at most one stone. Uh, can we remove it shares either the same row, the same column that has not been removed? Okay. Mm-hmm. Okay. Okay, so we are given with a stone placed at an integer corner where removes another stone. The stone that can be removed from the plane. So two stones are continuous. They share with this connection. Next beyond just pairs of stone with stone connect. Then all three stones, if any see or don't directly share a column, this again connecting component in a graph theory. Component connected component is a group of nodes where you can teach any node. Take a look at the illustration below. Yeah, connected component basically I can reach from any node to any node. Graph theory, coordinates forming connected components. That makes sense. Since every store in a connected component shares a row or column with at least one another store node, but the remaining store cannot remove as having all the other store. Therefore, if um total number of connected components, right? Max removable stones is minus number of connected components. Yeah, that was by my formula. All but one stone. Yeah, that's a proof. Uh, Inductive hypothesis. Okay, not interested in that. Sorry. Hold on too far. Represent the stones as graph. Mm, it's a data. Let's first search. Okay. Disjoint set union. You can find is efficient data structure for identifying connected components in a graph. Uh, Group elements into disjoint set. Determine which set belongs, which set and elements belong to, and merge sets. Exactly what we need here. If you are unfamiliar. Um, this to have a look at for in-depth explanation. We will begin by treating each stone as a separate set and meaning da 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 da. Also, each successful indicate two separate components are merged into one. Total number of separate components in the graph. The count is initial to n. A successful operation indicates. Okay. Set n is the okay. Initialize and union find. Set n as a size. Iterate over each stone. If stone share the same, if stone I share the same row or column, stone j perform union. Oh, okay. Mm-hmm. I think we missed something here. Yeah, we could do this really. Why we were, why we were like doing all this stuff for rowing and column. We can easily combine them into a single. for loop for lambda equal to 0 I less than n plus plus for equal to 0 j less than n j plus plus if stones I 0 is equal to stones of I1 same row or stones of wait, 0 stones of I1 is equal to stones of G1 then just DSU but union INJ right union is not equal to J J yeah we can do this right okay mm-hmm. I1 and J1 right is 290 J0 I1 mm-hmm. Mm-hmm. Let's run this okay but it's working now but why that was failing because we were are there something we were missing in that was there something we were missing in that set let's go this with we got the submission paste it now we have n columns we have n rows Mhm. Okay, I think we must be doing some mistake which I'm not able to figure out, but okay, now we get the solution. So yeah, we're good. So I'll stream again, right? There are some more questions left, like Kosaraju's algorithm is left, and some two questions on bridges in graph using Tarjan's algorithm and articulation point and Tarjan's algorithm. Some small concepts are left. So